Yeah, so I'm very glad to introduce Steve Weber, who is working at UC Berkeley with Professor Irfan Siddiqui. My understanding is that Steve's work is one of the first to really track quantum system through its evolution, ever since the 1920s. Yeah, and I'm very glad to give floor to Steve.
All right, thanks.
And please join us for the restaurant afterward. Yeah.
Cool. All right, so yeah, today I'll be talking to you about qubit state tracking near the quantum limit. And this work was done in collaboration with a number of other people, notably Kater Murch, who was a postdoc in our lab and who's now a professor at Washington University in St. Louis, and some theorists, the group of Andrew Jordan, who's at University of Rochester, and yeah, I work in the group of Irfan Siddiqui at UC Berkeley, the Quantum Nanoelectronics Lab. So just a brief introduction to quantum computing. So in classical computing, information is stored in a bit, and you can store information to two-state system, so 0 or 1. And in quantum mechanics, the two-state system is represented by what's called a wave function. And so it can exist in a superposition state, which is superposition of 0 and 1 with two complex coefficients, which are here, alpha and beta. And so there are a number of potential applications for quantum computing. For example, for factoring large numbers, Shor's algorithm, but also for other more scientific goals, such as simulating quantum systems, which might be useful in solid-state physics or in chemistry, and also for certain types of optimization problems. And there's actually a very recent paper by Seth Lloyd that talks about how you might be able to use a quantum annealer, a certain type of quantum computer, to answer certain questions in analyzing big data sets. So I think there might be a number of applications other than factoring large numbers if you could eventually build a quantum computer. So there are a lot of different physical systems that people use for their hardware to try to realize a quantum computer. One of the early popular ones was nuclear magnetic resonance. And one of the fields that's seen kind of the most success, some of the highest fidelities and precision, is in trapped ions. But the problem is with that field is that it's fairly difficult to try to scale these trapped ion systems up to larger and larger systems. The system that I've been working with are superconducting circuits. And these circuits are perhaps more easily scalable because you make them by the same nanofabrication techniques that are used in the semiconductor industry. So let's see, yeah. So that's the main advantages of using superconducting qubits. You can engineer the couplings between your qubits, or your artificial atoms, and the outside environment. But some of the difficulties or disadvantages of superconducting circuits is the challenge of decoherence. So these are also large macroscopic objects, and so they couple to the environment around them, and that can cause decoherence. That's a problem that there's been a lot of progress towards improving over the past 5 or so years. But another challenge is also is readout. How do you measure these superconducting circuits? And that's really what the focus of this talk is going to be on, and particularly the kind of interesting science that comes out that you can do with these systems. Okay, so progress in qubit readout. So superconducting qubits really require amplifiers to be able to read them out. And the reason is you have a very, very small electrical signal, a single quantum of energy, that you want to be able to read out. And at microwave frequencies, where the convenient frequency to make these superconducting qubits, that's a really tiny amount of energy. So in order to measure that energy with classical electronics, which are very noisy in comparison to this energy scale, you need to be able to faithfully amplify the signals. So what's called quantum limited amplification, and I'll talk more about that later. But there's been a great deal of progress in developing amplifiers to read out superconducting qubits. And this has enabled things like state preparation. So that's if you really strongly measure a qubit, and you can project it into one of its basis states, and then you know what state it's in after the measurement. So then you can then apply a simple rotation to bring it into whatever state you want. So good measurement allows you to do good state preparation. Improvement measurement fidelity is required for certain fault-tolerant quantum computing protocols, such as the surface code. And so that the surface code is a very popular approach to fault-tolerant quantum computing right now that's kind of being pioneered by the groups of John Martinez at UC Santa Barbara and by the team at IBM under Matthias Steffen.
My fellow Russian Alexei Kitaev who came up, and Sergei Graulik who came up with the idea.
Yeah, I think so. So yeah, and so experimentally with superconducting qubits, it's that's one approach that people are investing a lot of effort in. But in order to do that, you need to be able to very clearly distinguish between the states of your qubit. So you need a high fidelity measurement. Another thing is if you can have this highly sensitive measurement, you can think of then doing measurement-based feedback. So the idea of that is you take some measurement signal that tells you about what's happening to your qubit, and then you feed it back into your system as a control that lets you, for example, stabilize into some desired state, basically to fight decoherence. Also, this measurement has led us to investigate some physics, some fundamental quantum optics that people have thought about in optical systems, so like lasers and real atoms. But you can access different regimes of the same type of physics when you're using microwave systems, so like these artificial atoms or qubits, and microwave light, so microwaves. But what I'm going to focus on for today's talk is really how this progress in qubit readout has led us to some new experiments that have brought us to a deeper understanding of how a system evolves under measurement, or open quantum systems. So quantum measurement, just a simple summary. So the kind of quantum measurement that they teach you about in your physics class on quantum mechanics, that you'll see in the textbook, is called the projective measurement. And that means if you start with the qubit in some superposition state of 0 and 1, and then you measure it, at the end of your measurement, it's left in either 0 or 1. It's no longer in a superposition, and the probability of measuring 0 or 1 depends on the coefficients of your superposition. So that's basic. That tells you what's different about quantum measurement from a classical measurement. In a classical measurement, you can measure the state that the system's in, but in a quantum measurement, your measurement inherently disturbs the state of the system. So there's this measurement back action. Okay, so briefly I'm going to discuss some terminology of how we represent the state of a qubit. So I don't know if this is new to most of you or not, but so we have, I said we can represent it as this wave function psi, which is a superposition of 0 and 1 with the coefficients alpha and beta. And they're subject to this constraint, it's called normalization, that the amplitude squared of alpha plus the amplitude squared of beta equals 1. And so when you just have two complex coefficients that are subject to this basic constraint, without loss of generality, you can rewrite alpha and beta as cosine of some angle theta over 2 and sine of some angle theta over 2 with some phase factor e to the I phi. And so why this is useful is because it lets us represent the state of a quantum two-level system, a qubit, as a point on the surface of a sphere. And this was first conceptualized by Bloch, the theorist, a long time ago. But so basically the idea is this angle theta tells you about the angle in this direction on the sphere, and the angle phi tells you about the phase of your superposition, or the angle around the equator of the Bloch sphere. And so the basis states, 0 and 1, are represented as a point on the top of the sphere and a point on the bottom. But there's one more point that'll become important later in the talk, is when you're working with a real quantum system, maybe sometimes you don't know exactly what state it's in. Or maybe if you prepared 1,000 qubits, maybe you have some classical uncertainty in which state you actually prepared them in. And that's represented as what's called a mixed state, so pure quantum states are always going to be a point on the surface of this Bloch sphere, and that's imposed by that normalization constraint over there. But mixed states, where you have some classical uncertainty, can be represented as a point inside of this sphere. So they still have some coherence, but not as much. And so when you have a point within a sphere, you can represent it by just 3 numbers. It's a vector, so you can represent it by the x component, the y component, and the z component, and they're constrained by the edges of this sphere. So we call one of these a value of -1 and one of them +1. It's terminology from spins and magnetism. But the important thing is you just need 3 values, x, y, and z, and those tell you about the state of a quantum system. Any questions so far? Does this all make sense? Okay, so now I'm going to talk about this idea of quantum trajectories. So this is really the focus of our work is in how do you continuously monitor one of these systems, perhaps weekly continuously monitor a quantum system, and realize a measurement that's different than this textbook projective quantum measurement. In that it occurs over some slower time scale. You can actually track what the system's doing on a time scale faster than the projection rate. So the way you do that, you prepare the system in some known quantum state, and then you accurately measure its environment. So we can carefully engineer its environment, and I'll show you specifically what that means later on. But if you can actually watch this environment and see what's happening in response to its interaction with the system, then you can actually maintain complete knowledge of this quantum state as it evolves. And that lets you reconstruct the quantum trajectory, which is really just the path in time that the state takes along the sphere, this Bloch sphere that I showed you, as it evolves under continuous measurement. Okay, and then another interesting question that we chose to address, that really you need to be able to track these trajectories to answer a question like this, and so in our most recent paper we kind of showed how you can do this, is how does a continuously monitored quantum system get from some initial state, psi I, to some other final state, psi f? So these different colored lines here show different ways it could evolve in different iterations of a measurement. So you prepare the state 1,000 times, you let it evolve, it could go this way or that way or that way. And the question we want to answer is, what if we constrain the final state? I'll skip that point. So what if we constrain the final state to be just some particular final state, and then we want to know what's the most likely behavior, what's the most likely trajectory that the system takes to get from this initial state to this final state. So it's kind of an optimization problem, and I'll show you later on how we can answer that question using our simple system. So and the way we do that is by looking at distributions of quantum trajectories. So the really important thing here is that measurement in quantum mechanics is a random process. I said if we start in some superposition state and you do a projective measurement, you don't know if your result is going to be a 0 or a 1. You just know the probability that if you repeat it many, many, many times, that maybe some percentage of the time you'll get 0 and some other percentage you'll get 1. So here we want to actually repeat the experiment many, 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 many times, and each time we'll get a different quantum trajectory. But we can look at ensembles or distributions of these trajectories, and that's how we can kind of look at their statistical properties and learn something about the evolution of our quantum system under measurement. Okay, so here's an outline for the rest of the talk. I'll describe the physical system that we use to realize these measurements, and the type of measurements that we perform. They're called dispersive measurements. And CQED here stands for circuit quantum electrodynamics, which is based off of cavity quantum electrodynamics, which is I'll describe that in detail later. Then I'll show how we can use this system and these measurements to track individual quantum trajectories, and how we can analyze distributions of these trajectories. And at the end, I'll return to talk about a few potential applications of these ideas for quantum control or for efficient quantum state democracy.
Is that a computer simulation or actual data?
Actual data. Yeah. Okay, so I'll briefly describe the kind of systems we use. I mentioned that we can use superconducting circuits to realize artificial atoms. And what do I mean by that? Well, a real atom is a quantum system, so it has quantized discrete energy levels, and they're unequally spaced. So you can choose any two of those levels and call one of them the ground state, G, and one of them the excited state, E. And because they're unequally spaced, you can use laser light that's spaced at the frequency between those two. So in physics, energy and frequency are equivalent. So there's a certain frequency of light that will excite that specific energy transition. Now, the simplest kind of circuit we could imagine making is just an LC resonator, an inductor and a capacitor coupled together. But this is a typical example of what's called a harmonic oscillator. It's just like a mass on a spring or a pendulum. It has, and the problem with this system is that it has equal energy level spacing. So that means that, you know, all of these energy levels are equally spaced, so you can't address any one level with laser light, because if you tried to excite from this level up to the next one, that would be the same resonant frequency that would bring you up to the next one and the next one and the next one. So you can't isolate any two levels to use as your qubit states. So the next best thing to do is to make an anharmonic oscillator. So, and the way you do that is by taking this linear resonator and just introducing some nonlinearity. So now it's not a linear resonator anymore, and you can recover some of this unequal energy level spacing that you would see in a real atom. And the element that we use as this nonlinear inductor is called the Josephson junction. And it's a superconducting circuit element. So what it consists of is a superconductor, and then a very thin insulating barrier, and then another superconductor. So the dimensions of this are like 10 nanometers, or maybe like 100 nanometers by 100 nanometers by like a couple atoms, by like maybe 1 nanometer or something. So it's a really small element, but they're actually pretty easy to make using fairly standard nanofabrication techniques. And so the interesting thing about the circuit element is it has these relations that describe the, so basically a superconducting, this is kind of, I don't want to harp too much on these details, but basically like a superconductor can be described by what's called an order parameter, which is this delta here. And that's basically tells you about the macroscopic quantum state of this piece of metal. So a superconductor is a very special kind of metal that exists like in a well-defined macroscopic quantum state. And so, but since we have two different pieces of superconducting metal here now separated by this insulating barrier, they have two different macroscopic quantum states, and you can write a phase difference between those states, and that's what's delta here. And then these are just equations for the current and the voltage passing through and across this junction as a function of the phase. And I don't know if any of you are electrical engineers, but the point is you can kind of rewrite this as an inductance, and it behaves as a nonlinear inductance. And then if you put a magnetic field through, so if you put two of these junctions in a loop, a superconducting loop, then you can put a magnetic field through the loop, and that actually lets you tune the inductance. So this isn't very important to what I'll be discussing later. So
nonlinearity comes from sine or cosine.
exactly, yeah. So here you have some inductance, but then you also have this cosinusoidal dependence on this phase across there. So that's where the nonlinearity comes from, exactly. Okay. Yep.
Sorry. So I'm an electrical engineer.
Oh, great.
And I don't want to interrupt too much.
Oh, no.
So do you need to vary the magnetic field, or is it a static magnetic field?
So you can do either. So basically, if you apply a static magnetic field, then you'll get a static tuning of the inductance. If you apply an AC magnetic field, then you'll modulate the inductance. So you can do either.
So I can recognize the math, but also, so it's my understanding. So I learned about Josephson junctions, 20 plus years ago. Isn't it that the key property is that you can identify voltage and current across a non-conductive surface within the field, I guess. I don't know. Anyway, so
Yeah.
sorry to interrupt. Continue.
Oh, that's okay.
A nice picture.
So here's a picture of what they look like. So here we have one piece of aluminum, superconducting metal. Down here is another piece of aluminum, and there's a thin oxide barrier between them. So then you can have the charge carriers in your superconductor can kind of tunnel across that barrier, and that's how you get this current through the junction. And here's the loop that you can put a magnetic field from through to tune that inductance. And you'll notice the scale here. This is 500 nanometers. So these guys are just like roughly 100 nanometers.
Quantum tunneling.
Yeah, exactly. Okay, so now the TRANSMON qubits, that's the style of superconducting qubits that we use in these experiments. They're a really simple circuit. It's really just a capacitor shunted by one of these junctions, this nonlinear inductor. And so they have certain energy scales that I'll talk about in frequency, a capacitive energy scale of roughly 200 megahertz, and an inductive energy scale of roughly 20 gigahertz.
And the capacitor of the cavity in which you put the qubit, or separate?
So I'll show you physically later, the very next slide. Okay, and when you put these together, this paper describes the theory of exactly how these equations come out, but it turns out that this has a resonant frequency of around 6 gigahertz and an anharmonicity, or a difference in frequency between the 0 and 1, and then the next level of about 200 megahertz. So this is the system we use in all our experiments, and it works quite well, and a lot of other groups are using these to try to realize quantum computers right now.
So just a couple of things. So you can segregate the energy levels because they're a couple hundred megahertz apart. And so when you get this thing excited, I'm trying to visualize, if it's electrons, you think they're going to be bouncing back and forth doing like this. I guess we have Cooper pairs doing this instead. What's the characteristic time for these things to persist? Are these indefinite?
Like what's the coherence time, or like if you prepared a superposition state, how long would it maintain its coherence before? So I'm going to mention that on the next slide actually. So, but it's roughly 100 microseconds is kind of the state of the art for superconducting qubits right now.
So a long time as these things go.
Yeah. I mean, 5 years ago it was maybe 500 nanoseconds was the state of the art 5 or 6 years ago, and now we've progressed up to 100 microseconds. So
this is without sophos code, right?
this is without any kind of error correction. This is just the raw coherence time of the single qubit nowadays. Yeah.
There really is a parity in this scale. Right?
Yeah. I mean, so we can do coherent gate operations. So you can take the qubit state from the ground state to the excited state, or make some superposition state. We can do those on the order of 10 nanoseconds, 10 or 20 nanoseconds. So you can do a lot of those operations in 100 microseconds. Okay. So here's the physical implementation of our qubits, and so this is the style. This is maybe the less scalable version of it. But it's actually what gives you the best coherence times, and that's a long story which I won't go into. But so they're convenient for these experiments, but there are also people making them completely on a chip. Completely planar architectures that are perhaps more scalable, and they're starting to realize similar coherence times. But what we're doing here for our experiments, because it was easy, is we have a cavity, which is just an aluminum box, which has a well-defined electromagnetic modes or resonances, and so we can couple our qubit to this cavity, but I'll come back to that later. But the qubit itself is really just two metal paddles, so these are aluminum paddles, and they have some free space capacitance to each other, and that's the capacitance that I showed you in the qubit diagram. It's about 130 femtofarads, and then we have the Josephson junction in between them. So these are really simple, but you can make it all like on a smaller, more compact planar thing too, and there's been a lot of progress with that. And so this is the refrigerator that we use for these experiments. So in order to get superconductivity, you need to cool down materials. Aluminum is superconducting below a few Kelvin or something. But more than that, you also want to get rid of all of the thermal fluctuations and noise that would disrupt your qubit state. So that's why we have to do these experiments at about 20 millikelvin. So
same as D-wave.
Yeah, the same as D-wave, exactly.
And when you were referring to the folks that have done this in a chip, that would be like D-wave as an example.
Yeah, exactly. And John Martinez's group at Santa Barbara is they do it on a chip, and yeah, exactly.
So I think it's fair to say that your stuff, just to look at it, looks a lot like D-wave.
Oh yeah, absolutely.
They apparently have been pioneering the infrastructure in terms of the
Scaling
silicon substrates and the crane-looking thing and the.
Oh, I mean, these deletion fridges were around
standoffs.
before D-wave. They're actually made by Oxford Instruments.
Right.
But yes, D-wave is investing a lot in the kind of cryogenic engineering and microwave engineering you need to build up a large-scale system like this. The one thing they don't have is good qubits. So with these, our coherence times are 20 to 100 microseconds. D-wave,
Like a true entrepreneur.
Or an academic.
They have the ability to manufacture stuff, and if one of these academic groups was to supply them with a really good digital qubit at decent coherence time, they would be able to run with the ball.
Yeah. I mean, the other thing is they're limited to a very specific architecture. It's not the full-scale quantum computing. It's not a gate-based architecture. And the difference there is basically their system isn't useful for solving all of the types of problems you could with a quantum computer. It's just useful for a certain class of problems.
QUBO.
Yeah.
You had about 10 talks on that.
Oh, okay. I see.
Yeah, but if your technology is overlapping with their technology,
Oh, yeah,
it looks
very
like
much so.
about 80% overlap.
Mm-hmm.
That's very interesting.
Yeah. Okay. So, now I'm going to discuss on a conceptual level the kind of how we perform these measurements. And the system that we use is this cavity QED, which stands for Cavity Quantum Electrodynamics. And this system was really studied in depth by the atomic physicists. So Serge Haroche's group in France were some of the pioneers in this. He recently received the Nobel Prize for this kind of research. But the idea is you have this very simple quantum system that describes the interaction between light, or an electromagnetic mode, and matter, or an atom, or in our case, an artificial atom. And so you can describe it, basically you have an atom, and it can decay into the external environment at some rate, gamma, and it can couple to the field of a single cavity mode. So it's sitting inside of some electromagnetic cavity, and it can couple to a single mode at a rate g, and that cavity can then decay into some transmission line or external modes, and you can measure what's coming out of the cavity, and that decays at a rate kappa. And so in quantum physics, we like to write down Hamiltonians. That's what this H here is. And this is described by the James-Cummings Hamiltonian, which just has, so the Hamiltonian describes the total energy of the system, and if you it's a matrix, and you can diagonalize it to kind of find the energy levels of your system, and to kind of understand the interactions that are going on. So the basic Hamiltonian for this just has this term here, where omega r is the resonant frequency of this cavity, and this is like the number of photons in the cavity. So you add more photons, more individual excitations to the cavity, and then it's going to have more energy. This term, this sigma z here, is like the z component of the qubit state that I showed you on that box sphere. So here we have, and omega a is the atom frequency, the frequency of our qubit, and so we have this energy term that's proportional to the state of the qubit in this sigma z basis. So like the z value of the qubit state. And then we have this interaction term. This is G, the coupling between the atom and the cavity. And what this does is it allows you to swap a single excitation, so like a single microwave photon, between the cavity mode and an atom mode. And so you can look at, so when they're dispersive, which means that the atom frequency is very different from the cavity frequency, then you can rewrite this Hamiltonian in an approximate form. And the important thing here is this term right here. So it looks exactly like the energy of our cavity in the previous thing, except that now it has this extra term which is dependent on sigma z, the state of the qubit. And so what that says is the resonant frequency of our cavity in this regime depends on the state of the qubit. So this is really useful, because that means we can now use a measurement of the cavity's property, its frequency.
You've got a method of magnification.
Yeah, exactly. So we can use the resonant properties of the cavity to infer information about the state of the qubit. So that's how we perform a quantum measurement in this system. And I guess the other important point there is this is an indirect measurement then. We can measure a light field that scatters off of the cavity. So basically you send some signal at the cavity, it reflects off the cavity, and you just measure the tone that comes off the cavity, and that tells you about the state of the qubit, but it's indirect. It's not directly hitting the qubit. And that is what it's very useful for realizing these sensitive measurements and for looking at the kind of measurement physics we want to see.
And how is this different from, for example, D-Wave and others are doing?
Okay, so D-Wave I think is using some type of destructive readout. So what that means is that, so you know how I said in the ideal textbook quantum measurement, you measure your quantum system, it ends up in a certain state, and that corresponds to your measurement result. So you know what state it's in after your measurement. It just corresponds to your measurement result. There's a term for that. It's called quantum non-demolition measurement. In reality, a measurement doesn't have to be like that. You could measure what state the system is in, and then completely destroy the state of the qubit in the process of measuring. So like, and I think that's what their measurement does, which means if they wanted to perform a repeated measurement of the system, they would have to reinitialize the state. They can't measure it, see that it ended up in this state, measure it again, and be like, yeah, it is in this, it's still in this state after the measurement. They can't do that.
They set up the couplings between qubits and then run 1,000 iterations.
Right, right, exactly.
Because they indeed, as you said, it's
so,
the state.
So I think for certain, for certain kinds of protocols you would want to do, it's better to have this non-destructive measurement, because maybe you want to gain some piece of information by monitoring some syndrome qubit or something, but then afterwards you want to be able to immediately use that qubit again without having to reset it. And so that's why it's kind of useful to have a measurement scheme like this.
Are there times when the other approach, the D-Wave approach you're describing, is it better?
So I mean, up until a few years ago with superconducting qubits, because our amplifiers weren't very good, we could not get a very high fidelity measurement using this technique. So you could get a much better measurement fidelity using these destructive techniques. But nowadays we've made a lot of progress in the amplifiers, so now we can get pretty good fidelities with this kind of technique. So I mean, at the end of the day, that's the most important metric in a measurement is how faithfully can you distinguish between the ground and excited state. And especially with the results from John Martinez's group, I think they're getting multiple 9s. It might be 3 9s of measurement fidelity, the ability to distinguish between
non-destructively.
Yeah, non-destructively. Exactly. Yeah. Okay, so I kind of mentioned this. We can use a measurement of the cavity properties now to infer information about the qubit. This piece I drew here is a microwave circulator. It just says if I put a signal in here, it can only travel in the direction of the circle. So it bounces off the cavity, and then it passes through here and goes that way off into the rest of my experiment. It doesn't go back. So the basic idea is we want to look at a signal that's reflected off of this cavity, and we can measure its phase, so the phase of the signal that reflects off. And so this is just a picture of the phase shift as a function of the frequency that we excite the cavity with, or that we measure with. So when you cross the resonance, you have a phase shift. And so here, if the cavity frequency is at 2 different frequencies, depending on which state the qubit's in, then you'll have 2 different phase shift curves, depending on which state it's in. And so if we sit at a particular frequency, this omega d right here, which is in between the 2, and we just measure the reflected phase, then we would get 1 phase. So this is the signal we put in. And this is a phasor diagram. It's basically a way of representing the signal where the phase is now like the phase on this circle, and the amplitude of the signal is how far out you are. So your signal will acquire some phase shift, and the phase shift it gets will depend on the state of the qubit. If the qubit was in the excited state, after it reflects off, your phase will be up here. And if it was in the ground state, after it reflects off, your phase will be down there. But what allows us to realize these weak measurements is the fact that there's inherent uncertainty in the phase of these signals. And that comes from the quantum fluctuations of the electromagnetic field. So any kind of electromagnetic signal is going to have some random fluctuations in its phase and in its amplitude that are inherent to quantum mechanics, and those are called vacuum fluctuations. And at these very tiny energy scales where we're working, those fluctuations start to matter. So they can kind of be represented as these uncertainty circles, and you see that the uncertainty circle for the 2 qubit states can overlap. And that's what lets us realize these weak measurements. Okay. Oh, but the other really important point here. How am I doing on time?
Does anybody care?
Nobody cares.
Okay, good. All right. So basically, the difficulty here is that these signals. So this amount of noise here corresponds to quantum fluctuations at 6 gigahertz. But if you want to send these up to room temperature, the thermal fluctuations just of an environment at 300 Kelvin, at room temperature, are going to be way bigger, way bigger than the scale of these fluctuations. So you'd never be able to distinguish between these 2 states. So what you need to do is very, very sensitively amplify this signal so that when you add noise on top of that, it doesn't get in the way of the signal you're trying to see. And so the device that we use for these, they're called Josephson parametric amplifiers. So parametric amplifiers have been around for a while. The ones we use are fairly new. So using superconducting circuits to realize parametric amplifiers really only happened within the last 5 years or so. And so the amplifier is shown here, and it's just a nonlinear resonator, just like our qubit is. It's got a capacitor, and it's got an inductor. It just has a somewhat different energy scale, so it behaves more like a classical nonlinear resonator than a quantum nonlinear resonator. And so it has this resonant response. So basically, if this line represents the resonant frequency as a function of the power that we drive this resonator. So if you put in some strong signal tone at some frequency, we call the signal, or we put in some strong pump tone at a certain frequency and a certain power. And so we watch the resonant frequency bend backwards as a function of pump power until it gets to some point, and this is called the bifurcation point. And beyond that point, there are actually two different bistable states. And so that was a version of an earlier parametric, an earlier amplifier that actually Irfan Siddiqui, my advisor, was one of the pioneers of this device. It's called the Josephson bifurcation amplifier. And that's one way of realizing like a digital latching destructive readout of a superconducting qubit. And it was one of the very early ways to realize a high fidelity readout of a superconducting qubit. But to realize these non-destructive readouts, we can't work in this bifurcation regime. We have to work down here below, slightly lower powers where we have this substantial nonlinearity, but we're not in the bifurcation regime, so the dynamics are a little bit more controlled. And so if we take a cut at a certain pump frequency, so we're just sending in a strong pump tone at a certain frequency, and we look at the reflected phase of a signal that you that you reflect off of this amplifier as a function of pump power, then you see some shift here. And the idea is we can use the steepness of this phase response here as an amplification mechanism. So the idea is if you put in a small signal in this direction, if this is our big pump pointing with this phase, so it's along that I direction right there, and then we add a small additional signal, then it'll cause a large change in the total power, so that'll cause a big phase shift of the output signal. If you put a signal in the opposite direction, you'll go in the other direction, and you'll get a big phase shift in your output signal in the other direction. So signals that are in phase with the pump are going to be amplified. But you can have signals instead that are what's called in quadrature with the pump, and that's just they're 90 degrees out of phase with this pump tone, and they're actually de-amplified. So this is what's called a phase-sensitive amplifier. It only amplifies signals in phase with it. Okay, so here's what physically, those are the capacitors. We make them on silicon. It's a silicon nitride capacitor. We make Josephson junctions. We put them on this kind of hybrid microwave launch that looks like that. Okay, so now I'm going to show how we can use this measurement setup and these types of measurements to track the state of the system. So here's the full setup here now. So we have this measurement tone. It comes in. It bounces off the cavity, passes through here. We can couple in some strong pump tone here. And then both those tones go and reflect off of this amplifier, and then they leave to further amplification. This first amplifier is the really critical one, because there are commercial semiconductor amplifiers that work at about 4 Kelvin that do a really good job, but if you want to work down at 20 millikelvin, you need this extra amplifier here. And as I said, we can amplify one quadrature of the signal, the ones that are in phase with the qubit state information, which is along this direction. So we can amplify that, and that de-amplifies this direction. So after the amplifier, this is what it looks like if the qubit was in the ground state, and this if the qubit was in the excited state. And then we can add on some more noise to this, and it won't impact things very much because we have a bigger signal now. Okay, so I'm going to kind of talk about our measurements now. Here's just some pictures of our fridge and our measurement setup. There's a lot of microwave components here. It's kind of hard to see.
Does anybody mind if I turn off one of these lights?
I believe.
The other way.
Which do you want, dark or this one? This is better anyway.
Put 1/3 of them on.
I got 2 switches, you saw both. You saw all the degrees of freedom we have available to us.
Yeah, so I mean the basic idea, here's what our fridge looks like. I showed you earlier what it looks like with the cans off. This is what it looks like when you put all the vacuum cans on. And here's all of the microwave electronics that we use for our readout. Okay, I'm going to skip this. So the basic idea here, so we can take that measurement signal that I showed you, and we can take the phase information of that signal, and we can turn it into a classical voltage signal that we can then feed into our computer and analyze, right? And so so that's what this VM stands for. It stands for this measurement voltage that we get in a single measurement, a single iteration of an experiment. But if we repeat it many, many times, because of these quantum fluctuations of the signal, we'll get many different results, and we can histogram those results. So if we prepare the qubit in the ground state, we get one histogram corresponding to one phase, and if we put it in the excited state, we get another histogram corresponding to the other phase. And so the basic idea is that we can use this information to tell us about the state of the qubit after an individual measurement. So here where these histograms are very overlapping, that's what's called a weak measurement, because it's only going to tell you something about the state of the qubit. It's not going to tell you everything. And then if you go to longer and longer integration times, so you take the signal and integrate it for longer times, then the width of these distributions gets smaller, and then you have more knowledge about what state the qubit was in. So here's what it looks like if you were to integrate for a sufficiently long time that you can really easily distinguish between these two qubit states.
So you started earlier by talking about 2-week time frames. When you say sufficiently long, what is?
Okay, so how long it'll take depends on how many, on how strong your measurement tone is. So how many photons you're sending in to reflect off the cavity. The time scale in our experiment, the time scale to reach a projective measurement like this is roughly 2 microseconds or something. And so we can, we can set it up so that we can take measurements in 16 nanosecond chunks, so like really short little time steps. And so we can track the evolution as you start to add up those time steps. If you break this up into little 16 nanosecond time steps, and then you look at the whole thing, and after 2 microseconds, you have histograms that look like this, and you know whether it was in the ground or excited state. But you can kind of keep track of all the information as you go. It's a continuous measurement signal.
Is that equivalent to saying that you're having, in order to improve your beat error rate, your state error rate, you have to decrease your transmission rate?
Your transmission rate?
Yeah, how fast you're transmitting your qubits.
What do you mean by transmitting?
You mean probably the sampling rate, right? The 16 nanosecond rate.
The 16 nanosecond.
16 nanosecond is the sampling rate.
Yeah, but if you integrate longer, then you
Right.
can separate.
Right, exactly.
You can have a better
Yeah.
knowledge, so you
Yeah.
can retrieve your information.
Yeah,
basically
yeah.
In a communication link.
Mm-hmm.
So, what's the fastest rate you can achieve?
Right, exactly. So that's a really important question actually, because that limits so what limits the fidelity of qubit measurements is errors that occur from the decoherence on the time scale of your measurement, right? And so if you can measure really quickly, if you can get to well-separated histograms like this really, really quickly, then you can have a really high fidelity measurement, right? And so the fastest, for these types of measurements, I think the fastest people have been able to get, for example, and the other thing is like the more, these are Gaussians, and they still have a little bit of overlap, right? The longer you go, the smaller the overlap and the smaller your error rate. So basically, people have been able to get up to, I think, a few nines of separation fidelity, which means that the residual overlap between these two is less than 1%, in about a couple of hundred nanoseconds.
Wow.
That's like the best people have been able to do.
And how much damage do they do to the residual qubit in the course of this measurement set?
So effectively nothing. Or basically, I mean, the trade-off is as you increase the rate that you measure, then you are increasing the back action. So the kind of the extra back action or damage that you're doing to the state. so the trade-off is basically you have some rate of error that's just given by the coherence time of your qubit, right? And then you have some rate of extra errors you're adding by, like, because of your measurement tone. And so there's a trade-off between the two to try to find the optimal time that you can measure for to have the lowest possible error rate. And so people who care about getting these multiple nines of measurement fidelity will do a very careful analysis like that when they're setting up their readout.
So essentially it's optimizing the rate of information transmission in terms of bits, right?
Yes, exactly. You want to get the optimal measurement information while imparting the minimal back action, basically, or disturbance. Okay, so I called this one a partial or weak measurement, this one a strong or projective measurement, and we can look in between and define some characteristic time scale. So this is just what you could call the time it takes to separate these histograms. So the time you would have to integrate for their separation to be equal to 2 times their standard deviation. So that's the time scale that we'll use to discuss. You know, that's when I was saying like in our experiments this is like 1 or 2 microseconds. Okay, so how can we take a weak measurement and learn about the state of the qubit after the measurement? we can use this procedure called Bayesian update. And so this is really just a classical procedure. It's statistical. It has to do with conditional probability. So I'll explain it. I'll walk you through it here. It's not really so scary. So the idea is we start by preparing some superposition state, and then we measure for some period of time. And then suppose in one individual instance of the experiment we get some result right here. So we just measure for some period of time and we get a result of 0.16 or whatever that is. And then we want to say, okay, knowing that this is what our grounded excited state histograms look like, and knowing that we got this measurement result, Vm, what's the state of the qubit after the measurement? And so Bayes' law of probability says the probability of A conditioned on B is equal to the probability of B conditioned on A times the initial probability of A over the probability of B. And so we can do that for, in our case, that's just saying that the probability that the qubit is in the state 0 after a measurement result of Vm is just equal to the probability that we would get a measurement result Vm given that it was in the ground state. So that's just that blue histogram there. Times the probability that it was initially in the ground state, so that if we know its initial state, we can do this, times some normalization factor. And so you can basically just combine these two to get the, I changed notation here. Then basically you can write down an equation that tells you the state of your qubit after a measurement like this. Okay, so we can now kind of use this. I'm defining, so X, Y, and Z are just, when I showed you that box here, there's, Z tells you where you are here, X over here, and Y over here. And so you can, using those Bayesian equations and using the parameters of our system that we carefully calibrate separately, you can make predictions for, based on some measurement result, what's the state of the qubit going to be after measurement. So Z here is the qubit state in the measurement basis. So that means if we get a really large value of Vm, then we're sitting way on the edge of this histogram, so we know, okay, the qubit's in the excited state after the measurement. If we get a really small value, we know, okay, it's in the ground state. But if we get something in between, then it's actually just somewhere in between after the measurement. And let's see. So, and then we can experimentally do this. So check this. So we can make this prediction based on the theory and the parameters of our system. And then we can perform the experiment to see if we get the same results. And to do that, we have the sequence that I showed up here. So we perform a strong projective measurement and only keep the instances where we measured a 0. So that's, and effectively, we're preparing the ground state. So we have a whole ensemble of iterations of this experiment where we start off in the ground state. Then we can prepare a pulse that brings us from this ground state up to the equator of this sphere. That's what that r pi over 2 of y is. It just brings us up to the equator. Then we can perform a weak measurement for a period of time and digitize that measurement signal. Then we can perform additional pulses followed by strong measurements. And that's a procedure called quantum state tomography. It basically says if we apply no second pulse there and just do a strong projective readout, then that tells us, and we repeat this many, many times, then that tells us the average value of z. So if we start off right here and perform a strong measurement 1,000 times, half the time it'll say we're up here, half the time down there, so the average value of z is 0. But if we want to measure x instead, then we can just apply a pulse. So we can say, okay, we started off here, we apply a pulse that brings us up to here, and then we measure in the z basis, and we'll see, oh, all the time we got up here, that means that x was initially 1, or that it initially started in x. So that's just the procedure that you use to verify or validate the state of a quantum system. So, and so we can do that procedure, but now we can separate out each individual iteration. We can say, oh, okay, we want to only look at the subset of these many repetitions where we got some particular value of Vm, because we had this weak measurement result in the middle. So we can say only if we got a measurement result in the middle of 0.5, we'll average together the tomography results from that subensemble and see if it matches with what we'd expect based on theory. And here's what the experimental results look like. They match very, very nicely with the theory. So that tells us that we really understand what's going on in our measurement. So now we want to make use of the fact that this signal is actually time continuous. So we can prepare some state, we look at this measurement signal, and rather than just integrating it over the full period of time, we want to actually make use of this whole continuous signal. So here's an example. It's mostly a noisy signal. It'll just be this noisy trace in time. But from that noisy signal, we can do this same kind of Bayesian analysis and infer that the state of the qubit should be this as a function of time corresponding to that signal. So in this case, after about 1 microsecond, in this particular iteration of the experiment, the qubit was ended up projected up here to the excited state. At least that's what we think is happening, but now we want to prove that that's actually what's happening. So we can do a similar conditional quantum state tomography experiment to kind of verify that similar measurement signals give us an ensemble of similar measurement signals will give us a similar trajectory. And we can do that and we see, okay, they match quite nicely. Okay, so another thing here is, so all I've talked about so far is measurement dynamics. We can also add evolution, so some type of like, it's called unitary evolution, when you basically apply some resonant drive to your qubit that causes additional dynamics, and that makes kind of the trajectories more rich. But I'll come back to that later when I show you some of these ensembles. So we're getting towards the end now. I'm just going to show you, so now we can repeat this experiment 1,000,000 times. And we get 1,000,000 different trajectories. Some of them are similar, some are different, but we want to kind of look at their properties to really understand how does this system evolve under measurement. So here's with no extra drive, so just with only measurement going on. And so the color scale on these plots, so the kind of noisy colored trajectories there are just example trajectories to show you what a few of them look like. So this z here is the qubit state component sigma z. And then the black and white scale on the back is just an image plot that shows you the histogram of all of these trajectories. So black is a parameter. Black means that none of the trajectories passed through that point in phase space, and white means like the maximal number of trajectories passed through that point. So you can see here that they all start out in some initial state that we put them in, that we put the system in, and then you get a bunch of different trajectories that all kind of spread out in different directions. But after a long enough period of time, the qubit is either in this state or that state for the most part. At least on average. Okay, and so now we can look at this little toy question that I kind of mentioned briefly at the beginning, which is what if we pick some particular final state and we want to look at only the trajectories that ended up in that final state? So this trick is called post-selection, and it can maybe tell us something about the dynamics it would take to get from this state to that state under measurement. So the way we do that is only looking at that subset of our million trajectories. So in this case, it's like a couple tens of thousand, no, maybe like 10,000 out of the million trajectories ended up in this bin here, and then this is the shape. You know, the distribution of trajectories that get you from this point to that point looks really different from what you see otherwise. And those lines that I drew through the middle, one of them is a theory line and one of them is an experimental line for the average or most likely trajectory that would get you from one point to the other. And so you can think of that kind of like as an optimal path between two quantum states.
Steve, what are those steps on the top of the plot?
Those are actually, right, so that's actually just some binning.
Binning?
Yeah, basically.
And the strips as well come from that binning.
The which?
The strips, actually, if you go back one slide, you will see the strips. Yeah, right. Here are the strips.
Right.
Yes, that's really just binning. So I didn't have enough resolution to, so the time steps are in a resolution of 16 nanoseconds on the scale, and the vertical steps are I think there's maybe just like 100 or 200 bins vertically, and that's all the data we have to be able to look at, basically. But that's what the strips are from. Okay, so now we see much richer dynamics when we now add this extra unitary evolution in addition to the measurement. And so here, let's see. So on average, what this is going to look like is this purple curve here. And that's something that's very familiar to people who do quantum physics or atomic physics. It's called a Rabi oscillation, and that's just the average behavior of the state of a quantum system under a drive. So if you apply this drive, you would expect that. But when we look at the ensembles of, and when we average together all of our trajectories, we see that it matches with what you'd expect. But now we have more information than just that average value. We have all of the individual trajectories. And so we can look at them, and here's what it looks like. And you see that like most of the trajectories, so here I've turned up the measurement rate. So now the measurement time scale is 350 nanoseconds, that's shorter than before. And then this extra evolution, this driving or rotating around the sphere, is occurring at a rate of like 1 megahertz. So that's a little bit slower than our measurement rate. And so what you see is that initially the measurement is going to project you or pin you, and because you have that little extra nudge from the drive, almost all of the trajectories, or most of them, are going to end up getting projected by measurement down here to the ground state. But then after some time, your drive is going to actually no longer make it so favorable to remain in the ground state, and you can get projected back up to the excited state and down. So that's kind of interesting. And then we can apply these same tricks now to look at post-selection. So here we can change our post-selection time too. So we can see in a certain amount of time, what do the trajectories look like that get us from this initial state to this final state. And then, so let's see. So for a short time, they're very tightly clustered. So there's really like one optimal path that gets you there. For a longer time, they start to spread out more. And then this longest time here, you see they start to look pretty similar to like the full ensemble thing, but you know the exact shape will depend on the final states. Okay, so I can talk quickly about potential applications to these kind of weak measurements where they might be useful in quantum computing or quantum information science. One is the idea of quantum state steering through adaptive measurements. And there was recently a paper about people who did this using nitrogen vacancy centers in diamonds. So there's like defect structures in diamond crystals that you can manipulate like a qubit. And so they perform adaptive measurements, which means that you're measuring the state of the system weakly, and that tells you a little bit about what the state was after the measurement. And then you can change your measurement. You can feed back and say, okay, well now I want to do something different about the way I'm measuring, and by continuously doing this adaptive process, you can actually prepare a state without ever doing a projective measurement, just by doing these adaptive weak measurements. So then you don't need any extra like coherent pulses to prepare a state. So that's one interesting idea. Let's see. So another idea is, so as a new method of doing quantum state tomography, you're trying to read out the state of your qubit. So the way that I showed you here, where you start with some unknown state and you measure it in this basis, and then you apply a pulse and measure it in this basis, and then you apply another pulse and measure it in the other basis, and you repeat that a whole bunch of times, and you can reconstruct what that unknown state was. The problem is, as you go to more complex systems that have multiple qubits that are all entangled, so if you wanted to build, move towards building a real quantum computer, it becomes really prohibitive, or cost prohibitive in terms of resources to perform quantum state tomography in this gate-based way, the traditional way. So there are some ideas for ways you might be able to realize more efficient tomography that scales better with the size of your system, by instead using weak measurements and some combination of drives that let you like simultaneously probe it in different bases. So there's some theoretical ideas about that, and I think we're going to try in our lab within the next year or two to start looking at experiments to see if that's a valid idea. And then, okay, finally, maybe we can use this idea of most probable trajectories that I showed you, where we find the most likely path between two states. Maybe that information would be useful, at least the more general theory of it, that we kind of confirm the theory with our experimental results here. Maybe that theory is useful for developing quantum control sequences and things like that. Okay, so in conclusion, I'll just kind of summarize what I've been talking about. So I've mentioned that we can faithfully reconstruct the quantum trajectories of a superconducting qubit. That's the typo. Superconducting qubit. We've analyzed distributions of these trajectories, and we can use post-selection, only looking at some subset of them, to find optimal paths between two quantum states. And this validates that general theory that our collaborators came up with, which might have other applications. And it might suggest these new methods for quantum state preparation. There are some other directions that I haven't directly addressed because they're a little bit technical, but there's a matter of the ultimate efficiency of your measurement, which is like how well do you know the state after the measurement in a weak measurement, which is a much more subtle question than how well you know the state after a strong projective measurement. So we want to understand those issues better, because they're kind of essential if you want to do any kind of measurement-based feedbacks, and use this for measurement-based error correction with these weak measurements. Yeah, so that's everything. Thank you very much.
Yeah, please ask questions.
Could you comment on the amplification stage, on the noise introduced by the amplification operation?
Parametric amplifier.
The covariance introduced by the amplification.
Okay, yes,
Yeah, that's a
exactly.
question.
So that's a really important question, and it kind of, so basically, fundamentally, there's a quantum limit on noise that you can add with an amplifier. Any kind of amplification process is going to add half of a photon or half of a quantum of noise if it's a phase-preserving amplifier. But that noise can work out in some correlated way where you're not actually losing any information or having extra back action because of it. So there's some quantum limit that says the best you can do, your amplifier is not going to mess up your process at all. You can still maintain perfect knowledge of the signal you're trying to measure quantum mechanically if your amplifier is perfect, right? And if you're trying to do a projective measurement, so like a strong quantum measurement, you don't need your measurement efficiency or your amplification process. It doesn't need to be perfect, because you can just measure for longer. You know, when you project, the act of measurement is like projecting your qubit. Yeah. So I think basically the idea is when you're doing a projective measurement, suppose your qubit starts off in some superposition state. So this is, the ground state, and this is the excited state, and this is time. If you're doing a projective measurement, if you can always just measure longer and project more. So if you're losing some of this, so we like to think of inefficient amplification, inefficient measurement, as you're just losing some information about the state of the qubit that you would have been getting if you had a perfectly efficient measurement. So when you lose some information, maybe instead of projecting after this period of time, suppose your path is efficient in your amplification, then maybe you would look at the same trajectory and it would take you this long to be able to project it. But if you can measure long enough, if you can spare all that's going to do is cause you to lose some nines in your measurement fidelity. So for a projective measurement, you don't need a perfect measurement efficiency. For these weak measurements, and if you want to do any kind of measurement-based feedback and these kinds of things, now it does start to matter. And if you do start to want ideal measurement efficiency. And in our experiments, we're halfway away from the quantum limit of measurement efficiency. So we have a measurement efficiency of 0.5, which is about the best that people have been able to do with superconducting qubits.
So the amplifier specification you're using is like a noise figure of 3 dB? Is that what?
Let's see, it means we're adding half a photon of extra noise, basically. Yeah,
So the
bandwidth is low.
The bandwidth is a separate concern. The bandwidth of these amplifiers is fairly low, but it's not too low. I mean, it's basically the amplifiers like the ones that I show you have about, I think like 40 megahertz of bandwidth.
So that's the relevant noise figure.
Well, that's one thing that factors into things, but there's this extra figure of added noise, which is independent of bandwidth.
So if I understand, the amplification has a direct greater effect on the system, quantum system. That's what it's
yes. So I mean, it affects our ability to track the quantum system. So basically, the idea is, I mean, one way to think about it is we have some measurement tone, which reflects off of the cavity. So like in this picture I drew, we have this tone that comes here and reflects off the cavity and carries information about the state of the qubit. So suppose we put down some pulse and it comes out here and it carries a certain amount of information. It tells us, about the qubit state. But one way of thinking of this added noise or this inefficient amplification is, what if now we're coupling in, so if now we're losing some portion, 50% or something of this information, and it just disappears, right? And then the other half of the information we can take up and measure, right? And so losing this information about the state of your qubit after measurement makes it harder to do these kinds of weak measurements, basically.
I was wondering, if the measurement is done at 16 nanoseconds, then you probably need 60 megahertz of bandwidth.
Yeah, 60 megahertz or so, right? Yeah.
Yeah. So this thing's running at like 20 millikelvin.
Yes.
Yeah. So the relevant thing is that the noise at 20 millikelvin is just about equal to the bandwidth parametric noise introduced by that bandwidth. So it's nice. It's possibly not a coincidence.
Yeah, I'd have to think about that somewhere.
Yeah. So yeah, you're really optimizing the noise performance of this thing.
Exactly. Yeah. That's. And
how about the saturation?
How about what?
The saturation.
Oh, the saturation. Okay, yeah. So the amplifiers that I showed you here saturate at about 40 photons of measurement signal, which is like minus. I don't know off the top of my head, like maybe minus 110 dBm.
Wow.
Something like that. So these are very small signals, but we're actually developing new amplifiers that are traveling wave parametric amplifiers, we call them. And so instead of a reflection device, it's a transmission device, and it's actually this nonlinear transmission line that has a bunch of nonlinear inductors and capacitors kind of that form unit cells. And so that amplifier has a better saturation power, a better dynamic range. So that's about, I think it's maybe minus 100 or minus 90 dBm. So which is, you know.
Totally. So the saturation affects the trajectory of your state, right? It changes totally, especially
no.
linear.
Okay, so let's say, so saturation of your amplifier is going to affect the fidelity, or the efficiency of your measurement. Basically, it's going to distort your signal or something. But if you operate with a signal that's smaller than your saturation power, then you can still have an ideal measurement. So basically, we have to use a smaller measurement signal. So actually, maybe I'll draw this picture. It's kind of.
Is the architecture similar to like a traveling wave tube?
Which one? The traveling amplifier?
Wave tube, like it's used for satellites transmission?
I don't think so, but I'm not very familiar with those, so I couldn't say for sure. But what was I going to say about the power? Basically, you know, I said we have these, you know, this phase shift here that we're trying to measure, and we have this uncertainty here. So if you want to get a really high fidelity measurement, this is like we said, if you measure with more photons or more power, for the same phase shift, you have a larger separation here. So then you can more easily distinguish between these two. But ultimately, the amount of power that you can use for your measurement is going to be limited by the saturation power of your amplifier. So that, you know, you can't put in a bigger signal here than your amplifier can handle. And so if you have amplifiers with a better saturation power, then you can perform a higher fidelity measurement as long as you're not limited by other things, which there are other things.
I'll ask a quantum jump question. What is the next, the possible application once if you succeed with all these things? What is the first application you think?
For a quantum computer?
Messaging, or what do you think of that first one?
That's a good question. I mean, the reason there's so much research money being invested in quantum computing is because there's a clear application in breaking RSA cryptography, factoring large numbers. So I mean, I imagine anybody who puts in so much money to actually build a quantum computer is probably going to want to make sure they can do that with it. I mean, but I mean, I think there's all sorts of other.
I think simulation of chemical.
Yeah, simulation of chemicals and of solid state systems. Like maybe if you had a quantum computer, maybe you could simulate materials that you could use for high TC superconductors, for example, is one thing. So like there's a whole field of physics. They're trying to make superconductors that work at room temperature. Yeah. And they're close. They can make ones that work at liquid nitrogen temperature, but nobody has any idea how you can make one that works at room temperature. But maybe if you had a quantum computer, you could simulate those materials better, and you could do that.
Well,
maybe.
Yeah, I've been recently working on algorithms for the traveling salesman problem, and I'm getting numbers like for 32 cities I would need 100,000 qubits, net qubits.
Right.
And yeah, it's very clear that there's a lot of unsolved problems, you know, these various NP-complete problems in just plain old computer science that have been around for decades that you'll be able to solve with brute force algorithms.
Yeah.
Just insanely large amounts of superposition.
Yeah. And that's one field where I'm not really much of an expert in you know, these computational complexity classes and how quantum computing is useful for specific algorithms, but I know there's plenty of, you know, a lot of people thinking about those kinds of things.
It's conceptually very simple. If you have a thing with the best current algorithm is to compute some function 2 to the really big times, you know, which would take you a couple of 100 billion years on the current computers. Then being able to do it.
You said that 100 billion years?
Yeah, there's
It's real.
oh yeah, there's algorithms that would require that.
Pattern equivalent that you can do that.
Yeah,
It's very easy to write such an algorithm. It's much harder to write an algorithm that will solve it in a few seconds.
Right, but the thing is, with these are actual problems that have been around for decades, and they tend to have very unpleasant scaling characteristics. So that the traveling salesman problem, if you know what it is, scales exponentially with the number of cities visited. It becomes very large very quickly. And if you have brute force techniques where you just say, well, we'll just have, 2 to the 400 simultaneous data sets going through this system, and the problem then becomes figuring out which of the answers is the correct one.
Yeah, that's a good. It's one of the applications I can see.
There's a lot more stuff, but the big question is, at what point will this become, commercially feasible?
Right, and no one knows.
So in terms of your setup and that you have in the lab, what would be, according to you, what would be like the improvement, what the room for improvement and the areas where you would like to see, where do you want to take it from here?
Right, exactly. We'd like to be able to measure systems of, so in all the experiments I showed you today, there was just one qubit, right? And we were talking about measurement and how we can really carefully measure the state and what we can learn from that. But the number of things you can look at and the complexity of the problems gets a lot larger as you go to larger systems, right? So, I mean, specifically in our lab, we're looking to move up to, experiments with 5 or 6 qubits, for the near future, and like, so we want to build up, and other people have already gotten to that point who've been more focused, like, we're interested in kind of trying to think about the physics experiments that you could do to look at things like quantum measurement or quantum simulation or dynamics or things like that and try to see if there's interesting problems we can think about. And I think once you move to a handful of qubits, you can already look at a whole lot of new problems. And I think, but in terms of the larger efforts in the field and in terms of trying to build a quantum computer, the biggest things are like, it becomes a lot of microwave engineering, seeing how many qubits can you fit on a chip, how many control lines can you fit on a chip, how many, how can you try to read out all of these qubits sequentially or in a row, and like, it becomes, there's a lot of stuff that the people in academic research labs, like the one that I'm in, we try to avoid working too hard on those issues because it's the kind of thing that having a large coordinated effort with a lot of funding is like really good for, but it doesn't necessarily, get you a lot of papers out of it, get you a lot of recognition for the individual, grad students or whatever. So in our lab at the moment, we're focusing on, more concrete like science problems you can kind of like accomplish with a 2 or 3 person team, and like we want to make use of all the technological developments as they come and build up what we have. But I'd say we're less focused on the technological development itself in Irfan's lab than, for example, John Martinez's group would be.
Okay, let's give Steve
yeah.
And we can continue discussion over the dinner.
Yeah.
Thank you so much for speaking up, because I learned a lot.
Thank you.
as well.
I learned something.